Good morning, everyone, or afternoon, or wherever you may be in the world. Fabio, I'm sure it's in the afternoon, maybe even early evening in the UK. Thanks for attending. Uh, Today, this is a variation on a webinar I did almost 2 years ago on this program. And it's a question that comes up pretty regularly is how do you build a reliability plan? What are the elements that should be in one, and what are the considerations that go into crafting a plan that actually makes a lot of sense? And so I wanted to cover 5 basic steps that go into the process. And it's one of those things that it's part and parcel to what we do as reliability engineers. It becomes a an answer to the questions that we get pretty regularly. What's the budget? What do we need to spend in order to achieve our reliability goals? And oftentimes that's related to the sample size. And in many organizations and many programs that I've worked with, is the number of prototype samples used for reliability related testing often exceeded the use of prototypes for anything else. And as you know, those things can be really, really expensive. And then there's all the capital equipment and technicians and time and test and measurement systems and failure analysis that all goes into crafting and doing even just the testing part of a reliability plan. But the reliability plan is a whole lot more than just a series of tests. And as all of you know, it really cannot test in reliability any more than we can test in quality. It's really done during the design process. And so part of our plan is to make sure that the reliability related objectives are very, very clear and well understood throughout the organization. But what are some of the other reasons that you need a reliability plan? And so this is your first shot here at the chat window is, what kind of requests do you get? Do you get a direct request, or do you see the need to separate the document, or is it part of the regular program plan? Just a quick note is are you requested to create a plan, or is it part of the overall program? And you could hit a quick note, or if there's something else, is there another reason why we need a reliability plan? I think my favorite by far, though, has been when they said, well, it's required. We have to have a plan. So somebody created a plan and then they never looked at it again, but they checked it off the box. So I don't think that's a good reason to have a reliability plan. Yeah, and Brian, I agree with you, is that the design team, the electrical, mechanical, software, industrial, all of the various engineers are trying to get something to work. They're trying to invent a new product or a new feature set or whatever. They often do consider quality and reliability, yet they don't always focus on it. And so the plan certainly can help with that. Yeah, and Yvette, it's very true. It's what's the objective? What are we going after? And Fabio, you're right. Sometimes it's a part of our market. It's part of being qualified to sell into a market. I worked with the safety critical system once, and they had I want to say CSA, but that's not it. It's one of the European standards body, and the how they determine the quality and reliability of their products was a big part of how they got, whether or not they got certified to sell their products into the market. TUV, that's who it was. TUV, and I have no idea what that stands for, but that was a standards requirement. Well, let's dive right into it. I'm going to outline 5 basic steps here, and the first one is, I mean, this could be a webinar in and of itself, or a short book even. Uh, no wonder I don't know what it means, Joseph. Thank you. That looks like a German set of words. with lots of syllables. Um, well, the first step I think it was Yvette, you mentioned it, is, well, what's the objective? What are we looking for at the end of the day? And this often is should be less complicated than it actually is. Yet I've seen it mucked up so many different ways. So the first one really is, well, what is it it's supposed to do? What's the function? Now we may have to do entire documents listed for what are all the height, weight, color, feature sets. What does each button do? What's all of these different things that detail the engineering requirements for the document, or try to translate what we think or have been told by customers that they want. But it generally doesn't include an explicit definition of what a failure is. Now, oftentimes we say, oh, well, a failure is when it doesn't function. Well, the paint on the surface of a vehicle could be perfect, unblemished, no scratches, dents, aberrations whatsoever. Yet, if it's the wrong color, it's going to be considered a failure, in so many words, by a customer. They're not going to buy it, or they're not going to keep it for very long. So remember that failure is defined by the customer. And so the functions is our engineering set of requirements that says, here's what it's supposed to do, and here's what it's supposed to deliver. And oftentimes we stop at saying, well, if it doesn't turn the little green light on, that's a failure. Well, if the customer doesn't care about that green light, or that green light comes on at the wrong time, or it's in the wrong location, or they don't like it, it's still a failure, even though it electrically lit up. And so the first step is really take a step back and define what's a failure from the customer's point of view. And it's more than a function not operating from an engineering spec. So here's a piece of rope, and I've got a whole series of images of sailboats primarily, but let's say this is a piece of rope, or line, I should say. Well, what's its function? What's it supposed to do? And that's a positive way of saying it. And so use the chat window, and what would be a definition of this line? What's its function? And I'm going to use this example throughout as we're a rope or a line manufacturing company, a design and manufacturing company. So what would be a function of this line? Tensile force. Brian, that sounds pretty technical there. Barrier load, yeah. All right, see, very quickly we can think of a number of different things that go into this, right? And easily through the blocks. John, it sounds like you've been on a sailboat before, and I'm pushing my analogy a bit because I've seen them in the harbor, and I've been on one or two in my lifetime, so I'm going to be a little stymied for language here. Yeah, and Yvette, it depends. It's how's it going to be used? Is it for the controlling the rudder, or is it for controlling the sails, or holding the bumpers alongside the hull when you're at dock? So what's its function? And sometimes these lines can be used for all of those things. They may retire off of the mast and go to some other purposes, and then eventually made into a coffee table. It could have all kinds of things, right? So each of these things we're talking about are what's it supposed to do, and we can probably quickly define different technical specifications for each of those different functions. Now, it also has to operate in some weather, right? It's the effects of, and I use the word weather very, very loosely because it's also uh, chemicals, it's crushing forces. Say it's bouncing, the hull is bouncing against a pier, and then the rope is, or the line is what's separating them at that moment. It's crushed. It's all of the different forces, all of the different stresses that get applied to it. And it could be insects, it could be creatures, it could be uh, uh, all kinds of stuff, and all kinds of uses that these lines encourage. Yeah, mold and mildew. Yeah, excellent. Yeah. Um, And it's not just the simple thing of saying, well, what's the temperature range that it's going to see? And I know many of you've seen specifications for a product that say, oh, it goes from 0 degrees C to 40 degrees C, and it's operating temperature. And storage is say -20 to +60. And those are just points, kind of like specifications. The idea here, though, is um, let's see if I've got my drawing tool here. But I'm going to use temperature as an easy example. Is, as you know, temperature doesn't always exist at one point, right? Every day doesn't go to 40 degrees. And my 4 looks kind of sad there. And every day doesn't have a minimum of 0 degrees. And I'm on a C scale here. And while we might define a nominal or average temperature, say 20 degrees C, uh, or 15 degrees C if it's for the coast around here anywhere, the idea is that we define it much more carefully or more accurately by using a distribution. That doesn't have to be a normal distribution. It could be whatever it actually is. In this link I have at the top, it lists weather station data from around the world. And it's a great place to get hourly data or daily averages or monthly averages or climatic data. It has rainfall, wind speed, and a number of other weather-related data sets. But some things like mold or these other, like insects, uh, we may have to go out and do some measurements or get more creative of how to manage the stresses that are applied, the variation of those stresses. And so part of our reliability plan is to either reference a more complete set of stresses and stress data, which is a way more useful to our team than 0 and 40. Instead, we can say that uh, you know there's a percentage, some number, say 10% of our exposure to temperature may be above 10%, maybe above 40%, and there is some likelihood that we'll see less than 0%. And we can determine by a policy, for example, that we're going to design for the 90th percentile of our stress applications. Except in, say, safety issues, then we're going to apply a 99% stress load to our design considerations. But you can see very quickly that by adding a little more detail, I can start um, making the environment part of a reliability goal much, much more useful to the entire team. Now, in some organizations, they create an environmental document that lists all of these different variables and distributions and other considerations, and even breaks it out by different kinds of customers. So it becomes a whole lot more useful for making decisions than just a point. And this goes for temperature, but it also goes for use conditions. How often is this used? How often is a line hoisting a mast on a, a boat that's used only on weekends in this sailing season? So maybe 30, 40 times. And whereas others on a racing vessel may be used much more often, or on a charter vessel may be used almost daily. And so different markets will probably require different sets of just even temperature or the use profiles of how often something's used. And so the idea is to get very clear what's the functions and how do they fail, but also where and how it's used. Now, the last part is the one I see most often for starting a reliability plan is somebody says, well, what's the reliability of this thing? And hopefully nobody's thinking MTBF. Many of you I've seen before in here, so you know my opinion of that. But let's say that your program manager says, oh, 5 years. And well, what would be your comeback to your program manager or your engineering reference specifications defining reliability equals 5 years. What would be your next question? How would you get past that? Yeah, the probability. Yeah, yeah. I mean, what percent? How many should survive that long? Is it 90% survive, Brian, like you're saying, is 10% failure? Is that the 10th percentile point at 5 years? Or is that the 50th percentile point? Or are you expecting none to fail? And is that feasible, right? And in some systems, that may be possible, repairable and with high levels of redundancy. Your availability may achieve 5 nines availability over 5 years, yet you may still have failures. Yeah. And definitely go back to the definition of what a failure is. And it may change depending on what you're considering failures. There may be safety critical things that may have a very high probability of successfully operating and minimizing the chance of a single point failure, whereas other things are less critical and may have a much lower probability and maybe even a lower duration because they're repairable or replaceable. And so the idea here is, though, is that they're always in couplets, is always define the probability and the duration. And so if somebody says, I want high reliability, they may mean 99% will survive over some duration. But it's pretty meaningless unless you define over what duration. Hopefully that becomes pretty obvious. So let's say we've got this line. This is the application. It's used for, I think, trimming the sails, is if I remember correctly. And what would be a reasonable reliability goal for this part? So it has a certain tensile strength and ability to transfer a force across to trim the sails. So say that's its primary function. And it works on coastal regions around the world. And so we can probably imagine finding all the data that defines that. And it's used every day on this charter sailboat. But what would be the probability of success and duration? What would you start with? Yeah, the load, we could put that in the functions section. Yeah, I don't know, Bart, whether trimming the sails is safety related. I imagine if you don't have any other means of propulsion, it's probably pretty important. Also, if it snaps, you may have a safety related issue. Yeah. So now, John, you're talking about part of the weather, right? UV and salt spray and things like that. And you've got a probability. You've got 6 nines reliability. What's a couplet? What's a probability and duration? How would you phrase that for the reliability? If you were designing this line and selling it into this market, how would you define those last two pieces of a reliability goal? Depends, and I hear that a lot. We're getting loads, we're getting depends, different for different kinds of people. There's one part, 10 years with 99% probability of success. Now that's given the environment and function that it's intended to be used for, right? And it's a starting point, right? It's the what I found that if you're in a team that doesn't have a clear picture of what their reliability targets are, clearly fully defined objective, right? Is then do what Gene or Bart is doing here and just put something on paper and put it out there. Right? It's a start, and it starts that conversation. And it's now, Brian, I would accept the. I mean, you can put the probability or the percentile of customer use on there, but for the goal statement itself, the starting of your plan, a part of it is to start that discussion about what is it we're trying to actually uh, uh, create, and then to a large extent, how are we going to measure it, right? What do we mean by this? The other piece of this is, and I appreciate a little bit of struggle with this, is that it doesn't have to be a single point in time, and it doesn't have to be connected to any particular life distribution. And so, Gene, you're talking about the first 1,000 hours of use, right? And Brian, you've got 10 years, and I think there was another one at longer periods of time. Um, it also could be tied to cycles, right? The number of events that it adheres, or number of seasons that it's placed into use. It so you can define an early life duration. I want 99% to survive the first 1,000 hours, or I shouldn't say and 98% should survive 5 years, and 95% should last 10 years. Now, of course, those numbers are going to be defined by, well, what's the impact of a failure that happens early in the life of your product? The the impact on customer satisfaction and on your warranty tends to be a bigger, or on extra sales, word of mouth and all those things come from those early failures or get impacted from those early failures. Whereas um, the warranty period is a financial drain to your company, and so that may have its own specific goal tied to the financials. And then the expected useful operating life of the product may be much longer and beyond when you have a financial obligation to it. Yet your customers may expect it to work for 10 years and still maintain its functionality for its intended purpose. So define the appropriate sets of couplets. So it could be a line for trimming the sails, a certain diameter, tensile strength, load bearing, all these different specifications for it. In coastal environments and all of the weather and use factors that are associated with that. And then you could say 99% survive 1,000 hours, 98% survive 5 years, and 95% survive 10 years. That then starts the discussion of what we can use to create the rest of our plan. Now, I did spend a bit more time on this one than I expected, but it is that important, is get the goal very, very clear, because it really drives everything else. Yeah, yeah, John, I'm a climber, so I understand the idea. If you have a 3 meter fall, which isn't pleasant by any means, the rope does take quite a bit of shock loading, and so yeah, to be cautious, you should change it. I'd also consider changing the harness out too, depending on how you were attached to it. So another step, the second step of this, I'm going to go through these a little bit quicker, is modeling and the design for reliability elements of your plan. And so the first step is break down that goal. And the most common technique is to use a reliability block diagram, right? And here we're just dealing with, we have a system. Let's see if I get my pen to work. And I'm just going to list the numbers for a system here rather than try to spell these out, because it takes me forever to get a curved line with this pen for some reason. My pen likes doing straight lines, not curved lines. And for a line, it may be the material selection, it may be the terminations, it may be the weave that's used, it may be the assembly process. All of these different things may contribute to the reliability of the product, and each of those may have a separate goal in breaking it down. And as you know, in a series system, that any single point that fails can lead to a system failure. So if my overall system is at, say, 95% reliable over 5 years, then none of the separate components of that can be any greater than that, or any less than that in its reliability. So in this case, each one would be at, if we did just a straight line apportionment, they'd be at about 99% reliable over 5 years. because 0.99 raised to the fifth power, multiplying these 5 together, would give us about 0.95 overall. So it's a very simple concept, but it also then allows us to have that discussion with the team as to where's our risk, what elements of the system are most likely to fail. So maybe a navigation or a communication system on your boat, it may have circuit boards and a console and an interface and a microphone and a speaker. Now, if any of those fail, we likely lose the ability to communicate. And so the elements each then receive their own particular goal, such that if each achieves their specific subset goal, we achieve the overall system goal. But it allows the team to start negotiating back and forth and to understand the contribution of their part of the system to the overall system's reliability. Now, this is the simple model. There's other more complicated models out there. And depending on your system, though, you would be simpler or more robust. But once you have a goal, break it down so that the different elements of your team have specific goals for their part of their design focus. And allow it to communicate how important each of the elements is to the overall system. And so design for reliability, and we've been doing webinars for the last couple of years, and many of them related to elements of or pieces of a design for reliability. Now, one of the things I find that's very critical, though, is you got to let your team make decisions related to reliability. Many designers understand uh, failure rates and understanding the impact of a probability of failure will have on future field failures. What they often don't have, though, is what's the cost of failure, right? What's the ability of this line, or if it fails, what's the cost? If it fails under warranty, do we give them a new product? And then there's shipping and attendant costs to that, maybe some failure analysis, and maybe some other requirements that go with it. If you have nothing else, if you have no field data, and you have no way of tracking costs per failure, is just use a guide that I found useful in the past of 2.5 times the retail price. Now, your market and your business may change or be different from this, but oftentimes just a little bit of research, you can find, well, what's the cost of failure? And break that down to individual failures. That makes it useful for your designer so that if they know they're looking at an issue that has a 1% defect rate and they're going to ship 100 units, well, they're expecting one failure, right? Now, multiply that times the cost of a failure, and now I can make a judgment whether it's worth increasing the price of that component, say. If it's less than the cost of that single failure, it's worth doing. If it's more expensive to fix this thing and reduce the failure rate, any appreciable amount, well, then it's a business decision to not do this. And maybe one way that you're creating this trade-off. The other part is that the elements of tolerance analysis, and it ties into process capability and all these other elements that oftentimes we get involved with as a reliability professional. And so same goes for stress, strength, and derating for mechanical and electrical systems. But these are just a couple of ideas in the design for reliability part. What else is included in this? What would you recommend if you're designing a line, say, for a sailing ship or sailboat? What would you recommend goes into the reliability plan? And this is prior to getting prototypes. What would you recommend that we do from a design point of view that makes this work? Right? Customer use cases. We talked a little bit about that in the and goal setting event. How would you use that data? Now, Alejandro, HALT is a test, right? So this is prior to test. We have no prototypes yet. we're coming up, say, with a new weave, or we're coming up with using a new material, or whatever. What would you recommend the design team does that helps them make decisions related to reliability? Yeah, FMEA. We don't need protos for that. Modeling, simulations, finite element analysis. Um, yeah, yeah, Andrew, you were typing as I was talking, so I think you were ahead of me. You got it. Yeah, exactly. Is the other piece of this is it depends on what our team is capable of, right? If we don't have any finite element modeling tools and we don't have the capability to do that, uh, is it worth investing to get that skill in house, right? And how does that relate to the reliability part of it? But things like literature searches and historical reviews and maybe working on setting up experiments just on the bulk materials that we're going to use, understanding and characterizing the different variability elements that are going to be contributing to the reliability. All of those things start to contribute before we start having prototypes. And as you know, many of the reliability capabilities are determined before we get a first prototype. And so the idea is to create the right amount of information. So the goals, the environment, and all the use cases are all part of enabling your designers to make good decisions. And then the cost per failure is often a critical piece to that. What is it? What is the impact of a change in reliability? And it allows the design team to start balancing those decisions more appropriately, or more completely, I should say, than otherwise we're capable of doing. Right? So a couple of people mentioned HALT and FMEA, and those are tools that we start using in the design process between the initial design and concept phase and creating the FMEA and what could go wrong and the first sets of prototypes. But what we're really doing is looking for what's at risk, what could fail, all right? And so the FMEAs is the best one. Now, the wrong way to do this is to outsource it to somebody else so that they create a nice fancy report and it gets checked off and never looked at again. But consider your FMEAs. Are you doing them like voting in Chicago early and often? And anybody who's a history buff knows that's a joke. But it's get your suppliers involved, get your manufacturing partners involved, get your customers involved, and it's never done. It is one of these messy, ongoing documents that should be incorporated into daily discussions as much as you possibly can, right? Use the FMEAs to help you, the rest of your team, understand the risks and where do we need to focus our design effort, our simulations efforts, our prototype efforts, our testing. So let's say we have a line here that's holding this larger vessel to the line. What could cause that to fail, right? And I mean, besides, I'm not sure that's a pelican. I'm not sure what kind of bird that is. But just the bird, what would be the causes from birds being on your line? What kind of damages could they look at? Let's say we're focusing way in on a FMEA and looking at this kind of picture. We know it happens. What could happen? Yeah, acids, the talons or claws on their feet. They You've seen birds where they're always rubbing their beak and cleaning things. You might pick up a shell from the coast and sit here and try to crack the shell open, get debris into the fiber weave, and then its normal motion would act like small knives. Um, yeah, extra strain. Yeah, probably not a whole lot given the rating of this rope, but yeah, microbial growth. I hadn't thought of that. That's a good one. Yeah, yeah. The motion of the waves, the chemicals in the air. This vessel is probably not a sailing boat. It's probably a diesel of some sort. So petrochemicals, just pollution in the water, pollution in the air. Yeah, you got it. There's all kinds of different stresses that apply. And it's thinking through all of that. So if you happen to be in San Diego, California, have this beautiful harbor and all these things, you're familiar with one set of classes. But what's the harbor like on the East Coast or in Europe or in the Mediterranean or in Asia? What's the changes or differences that occur if you're in a different part of the world? Now, part of that risk identification and engineering judgment goes into then, well, where's the boundaries, right? Halt testing in and of itself is a way of determining where's our limits, what can happen. Now, the most important part of halt testing, or halt, is failure analysis, is understand why it fails. Yeah, and we're purposely going over the expected loads that our product is going to see, the different stress applications it's going to see. But many times those failures, once we understand them, show that they can fail in a similar way, but just take longer in real life. And so by taking action to minimize or eliminate those failures, it allows our product to become more robust and hence more reliable. So let's say we have our orange line here again. What stresses would you apply? Yeah. And John, you're ahead of me on this one, is the UV degradation, right? And the polymers that we use in more modern lines are very susceptible to UV. Polymer is not all that stable in sunlight, so there's usually lots of additives put in this thing. Um, yeah, so bending, rolling it over poly, cleaners, and say pressure washing even. What does that do to this thing? Remember the bird. How would you stress that, right? Or wet drying cycles. How would you do that? Salt fog, cyclic loading, um, all the temperature, humidity. Probably not going to use voltage like we would with other ones, but shock loadings, yeah. The tensile strength or crushing, either one. We can very quickly come up with lots of ways to do this, and then you have to back off, right? Map that back to the work we've been doing with FMEAs and engineering judgment, and what's in historical data. I think somebody mentioned, I saw it going by, is the field data. There it is, John. Is, well, what's caused our failures in the past, and how does this product map against those stresses? And so narrow it down to the ones that you really need to answer and go into the labs and start breaking things. That's always fun. Now, I used to work at HP, so we used to call things issues. There was a penchant to not label things a problem, because a problem is somebody's fault, and is kind of the way the reasoning went, I think. And so we had issues that we needed to solve. And so it's a semantics thing, and it's stuck with me over the years. But anyway, we find problems, we find issues, we find things that aren't quite right all the time during our development process and manufacturing and shipping. Keep track of those. Now, here's a quick math test for you. Let's say we've created 10 prototypes, and we get them back, and we start doing the initial evaluation of them. We're measuring things, we're testing things, we start putting them under some stress, and one of them fails for some defined reason. One of them fails. What's the result of that? What's our expected field failure rate if I had one failure out of 10, and it was one minor thing? Maybe we lost a couple of strands on one of the weaves. Yeah, we're still going to have to do the root cause. We're going to have to understand what exactly happened. But what's the ramification of having one of our prototypes fail? I picked really simple numbers here, so hopefully you can even do it in your head. Now, if you're fancier, you probably pull out a chi-squared calculator and do a confidence bound around it. Yeah, but I don't need a calculator or dealing with problem stats and confidence to say, well, I had 1 in 10 fail. And if we change nothing, the likelihood is, the most likely scenario is that our field shipments are going to have 1 in 10 of this similar kind of problem. And yeah, it's a sample, and it's a crude estimate of our population, but we only have 10 samples. That's all we have. That's all we know right now. And so as of right now, with the single failure, we have a 10% field failure rate. That's our estimate today. Now, sometimes our problems are intermittent, right? Electronics are famous for this. We have an intermittent problem or software. Oh, we only saw that once. Well, the same thing applies. If that issue or that problem would have caused a customer to say, hey, this failed, you now incur the cost of a failure, even if it was intermittent. Yes, intermittent problems are more difficult to resolve, to understand, to identify, and so on. They're no less valuable, though, to helping you improve the reliability. And so you might not use the word sale with your products, but do you ship with known issues? I'll leave that as a rhetorical question. Yeah, don't use mean time to failure. Yeah, chi-squared often implies, I agree with you, John, deals with exponential distribution, but it can apply to any point estimate of MTBF is also just a point estimate. All right, so one of the steps now is you've got a plan, you got a goal, you're doing apportionment, you've set up a number of tools like FMEA and HALT and maybe some simulations and some other activities, derating, stress strength calculations as part of the system. But how do you provide feedback to the team to keep them on track? Well, of course, there's estimates, and this ranges from just a straight out guess, right, to say, yeah, we think this will work, and but make sure that each of your estimates includes where it came from. How because a flat guess from is may or may not be as accurate as an expert opinion. And a Delphi method, if you're not familiar with it, is a technique to poll various experts in your field and to look for a consensus. Very briefly, what you do is say you find 10 people in your organization, you ask them, how reliable will this be at 10 years? And some will say a lower number and some will say a higher number. And then ask the ones in the extremes to, why did you say that? What information do you have that justifies your estimate? Share that back to the rest of the group so that you share the information that may change the overall consensus of where you're at. And as a way of predicting things, it's become a very useful technique to drive to a consensus of where your estimate should be. Now, notice I'm not putting parts count on here, these predictions in it, but I am going to talk about using physics of failures models, using literature of previous work on material sets, of using reliability growth modeling. Depending on your industry, you may be finding lots and lots of issues over time. Well, there's tools available for you to plot that and look at your estimates going forward and make a prediction about what your eventual reliability performance will be. Now, parts count predictions have a role, but they're not useful for making predictions, despite their name. They're used in comparisons and for order of magnitude at best estimates of are we in the ballpark, and even then it's pretty bad. But if I'm comparing two different systems and I want to get a relative judgment as which is more reliable, even then there's a lot of error. Whereas using understanding your failure mechanisms and modeling and simulating those things will probably give you a step up on predicting its future performance. And again, use that to update your reliability block diagram. Initially, it starts with just an apportionment. Here's our top down. Here's how good each of these systems need to be. Whereas estimates and predictions help us then to start narrowing down, are we on target or not, right? And then finally, we're going to do some testing. And we're going to do testing in all kinds of different areas. But part of that should be with an eye towards updating that block diagram. Keep the focus on providing feedback to the team. Are we there yet? If your vendors have good information, use that to update the block diagram. But for each section of this is to keep track of, well, how accurate or how reputable, I should say, is that estimate? And use that in two ways. One is what areas has the most uncertainty in your block diagram current estimate, and work to improve those estimates and maybe using a test or a better simulation. Whereas Other times you're going to get a number and it's just not good enough. Do I need more samples in the test, or is it really a risk and I need to change the design? Or can I shuffle the overall system reliability apportionment such that I can accommodate a power supply that's not quite as reliable as it could be or should be? It still allows us to hit the system goal if other parts are performing better. But start having those discussions, and it's that feedback mechanism that allows your team to engage with those reliability focused discussions. Now, as you go through this entire process, you're going to find things that are on the edge of being okay, and a little bit of variation from your supplier, from your manufacturing, or in its use cases are going to cause problems. And so you need to set up some ways to continue to monitor and track your progress towards achieving your overall goals. And so many of you know about statistical process control and capability and analysis. Keep in mind that it's best focused not on what your vendor or your supplier or your manufacturing facility is typically measures, or what they like to measure, or what they're able to measure. It really needs to be focused on what's important to the performance of your product. Now, I use critical to reliability. Some will use critical to quality. Others use critical components or critical functions of your product. Whatever it is narrow it down and focus on the process control on those areas that are most relevant to the future performance of your product. And so you may need to go 2, 3 steps deep in your supply chain to find the right place to make those measurements. But it's always strive to measure as far upstream or at the point where the variability causes the failures. So in those lines, those ropes, if the polymer vendor has too much variability in the base polymer, then the individual strands may have weaker areas and stronger areas. So by becoming more consistent in those polymer blends, I reduce that variability along the line, creating weak points in the rope. Use the control charts, not just for show, but actually use them to make decisions in the manufacturing process, for example. And in many cases, you may find yourself having to teach or mentor your vendors to get the most value out of that, both for them and for you as the buyer of those components. So here's a line, and here's somebody making a measurement on it, I believe. What would you monitor if you're making I think this is technically called a hauser, Hauser, which is like the line that attaches a ship to the dock, if I remember right. What if somebody's providing the material here for you that you then weave into this line? What would you monitor? Tensile strength. Yeah, John, that one's a lot of people don't like hearing that one because it's a destructive test. But yeah, elongation. It may strain the system. You may not be able to use that line, but you could measure it. It'd be interesting to see if the elongation has a relationship to the tensile strength, its ultimate deformation. Yeah, necking. If you're doing it on a single strand, not on the resulting weave, yeah, and if it's a fibrous based one, like a cotton or a hemp or something like that, the amount of fraying and how the ends are captured. Yeah, Karen, so the diameter, I agree. But again, each of these things is, as we learn about the product, which of these elements that we can measure is actually related to something that we care about. Yeah. So very quickly you can come up with dozens of different things you could measure, but it's then back to what's connected to the highest risk elements leading to failure in our products. Good. All right. Again, it's really keep track failure reporting and corrective action systems. If you're working with suppliers, you might call those corrective action reports. It could be formal or informal or whatever. But it really is important to deal with every failure and at least get it through the triage system. And the idea is that the failures contain the information that communicates back to us, are we on track? Did we achieve our objectives? Wayne Nelson once, I asked him, what's the best way to design an accelerated life test? He said, ship all of your products and monitor them to failure with your customers, because then you know a whole lot of information that allows you to create a really good test. Well, our reliability plans don't end at shipment. It ends at the eventual demise of every single product in the field. And failures that are out of warranty still contain a lot of information that we need in order to improve the product. So keep track as best you can. And one trick that I heard about some years ago was this group took part of their development team, the people most intimate with, say, the material science of this line materials we're using for our product, this rope. And every single initial failure in every single initial application of the product, they traveled to, obviously the bigger installations, or they were in a higher volume product, they would be at the call centers. So there was no delay in the right people getting as much information as possible. And then if it was the call centers, is that the as soon as it was a physical failure, it was identified. It was ship it back in the most expedient way possible. And the idea was to find those issues that we just didn't find during the development process and get those solved as quick as possible. And so a heavy emphasis on first shipments really does pay off in the long run if you've got some devoted resources to help make those changes and improvements right away. It doesn't stop there. Keep tracking this stuff. Keep revolving and isolating these things. We really don't want to be surprised by a vendor that says, oh, we changed something, but we didn't think it was important. And then our first real detection of that is a quick ramp in field failures. And so keeping track of the process, the vendors, the critical to reliability elements of our product with process control, but also monitoring the end results. Now, the field failures are defined by the customer, right? And a big part of our work in the reliability plan and in the tools that the reliability plan helps our overall group focus on is not necessarily does it function. It does it function well enough for the customer to say it's not a failure, or contrary-wise, is where's that boundary? Where do our customers define something as a failure? And let's make sure that that's interwoven throughout the plan. And so the basic process here, I didn't find a chart that had 5 elements on it. Otherwise, I should have used 5 because I had 5 steps here. But the basic steps are set a goal and then model it, the apportionment system, and make sure that those are clear with the couplets, the probability and durations in multiple couplets as appropriate for all of your major systems. Then it's focusing on the design for reliability. This is before you have prototypes. So stress strength and derating and simulations and FMEA are all excellent sets of tools depending on what you know and don't know going forward. The idea, though, is to identify those risks, understand what can cause the customers to call something a failure. Then track it. Are we there yet? Think of the kids in the back seat. Is feed the information from the many different sources we have available to provide estimates of our performance, reliability performance, against those goals and models. If we don't track it, setting goals is pretty meaningless. If we only track and test, but we don't have goals, again, it's not very valuable. So those two really, really tie together. Then as we learn through this development process, is Now we focus in on what we need to control, minimize that variability that affects the resulting process. And so whether it's UV or tensile strength or material variability, we want to make a good line that will have 99% survive for 10 years, for example, in a sailboat on the coast here in California. Now, going through these steps and tailoring that to what our team is capable of and within all of the constraints that we have to deal with is you can start crafting a pretty reasonable reliability plan. And remember that you're not the only one doing the plan. You're not the only person, resource required to think about reliability as the reliability professional on the team. The plan really does set the stage for pretty much everybody involved in creating this new product to consider reliability and make good decisions. That's really the outcome that we have in creating a plan, is to let the rest of the group create a reliable product. Oh, excuse me. My voice is going to go right there. Well, thanks, John. Have a great day. And so I'm going to hang out on the line here. I know we're coming up right on the hour. I did have a lot of material in here. I was a little worried about that, but I hopefully found enough spots there for your participation. And given the chat window's been buzzing along, I appreciate everybody's inputs and contribution there. But what are your questions? And let me pull up the conclusion panel here so you can get a copy of the slides if you like them. Over on the right-hand side, you just highlight it and click download. And it's about 12 megabytes. As you know, it's lots of images in there. So hopefully you get the idea that reliability is more than just the test plan. It really involves a good number of steps prior to getting to testing. And everybody's saying thanks. A great rest of your day and holiday season, all that good stuff. We'll see you again next month. Oh, and I almost forgot. I don't have a topic for next month. I haven't written the abstracts and programs for the start of next year. So if you have any ideas there, let me know. Anything you'd like us to talk about. Design for maintainability. Good one, Fabio. We'll have to put that on the list. I should probably get a guest speaker to join me for that. I do know some about design for maintainability, but I'm not an expert in it, so it may be well worth getting a guest speaker for that. See what I can line up. So is anybody in a part of the world where you can go sailing? Thanks for the applause, Gene. Appreciate that. Welcome, Fabio, and everybody. Going sledding now. Have fun.